So in this session, let's just do a simple and steady uh, slow motion calculation of actual covariance of x and y. So I hope you have reviewed the videos to understand the motivation of covariance x and y, because if you don't, doing this becomes very robotic. You don't understand why we do it this way, right? So you need to have that understanding of the motivation first. So go back to the video again to review if you haven't done so. Now, assuming that you have understood why we need covariance, so then in this case, let's just say that we have gathered the measurements of how many? 10 samples. So n equals to 10 here. All right. 10 samples, but there are 20 numbers. Why? Because for each sample, remember a sample can be a student, a property, a machine, a car, just an item in real life. A sample, we perform two measurements simultaneously. All right, so on the same sample. So here it can be anything. I'm just giving some random numbers here, but also kind of carefully crafted to make sure that there is it shows up as certain illustrative features. So for example, the numbers 8 and 9, they are repeated, yeah, but they are paired with different y values. So 8, 6 is not the same as 8, 7, for example. So in two variable measurements, in two random variable situations, or we call it two population situations, we look at a pair of numbers to see if they are the same. So we don't look at 8 and 8 and say, oh, it's repeated. We look at the pair itself as a distinct point. So there are also points that are repeated. So for example, here, right, 9 and 7. So you can think of, for simplicity, to help you understand, you can think of x and y as, what was it? X as a weight and y as the height. And adjusted to certain proper units. Of course, 8 and 6 doesn't mean anything here. But let's say they are adjusted to certain units. And we can understand why people with certain weights, 8, can have different heights, right? 6 and 7. Yeah, so it can occasionally be the case that a certain person has weight 9 and height 7, and yet another person also shares the same thing, right? It's not impossible. So that's just to illustrate these features in real life. So next question, how do we calculate the sample covariance? Well, strictly based on formula, right? So this is the part where you, number one, don't define your own formula. Number two, actually is way easier just to follow the formula, because you just mechanically do the calculations, right? So in the sort of most tedious, slow motion, and number by number way of writing it out, the calculation, it will be, we go through the first point, it's 8 and 6, right? Okay, so 8 minus off the mean of x. So the mean of x will be, you find this first column, you average out, and that will be the mean of x. And if you just do your sums, you get that this is 8.6. If you find the vertical average of y values, you find that it should be somewhere between 6 and 7. Answer is 6.5. Right? So we do that. So we multiply these two deltas together and then keep adding the same products from other points, resulting from other points. The sum total of it all is then divided by n minus 1, so 9. So end up we get negative 0.1111. So that's the slow motion analysis, right? So that you really gain a very solid feel that, yeah, the formula actually gives us the correct covariance of x and y. So it turns out to be negative, remember? What does that mean? Okay, you must think of the 2 by 2 LED matrix, right? So it is the second and the fourth quadrant that is being lit up. It's kind of like a negative gradient, right? A line with negative gradient. So that is what is trying to inform us. Now, the strength of it, 0.1111. Is it very large? Is it very small? Before you conclude that, hey, it's smaller than 1, let me caution you. Who says it should be compared with 1? Nobody says that, right? Remember the value, the unit of x and unit of y. It can be anything. So when you calculate their product, the resulting large and small size of the number becomes very hard to get a good feel with. So you really cannot jump to conclusion about anything at all, right? So other than the sign, we cannot say much. And actually, the sign itself is also a bit dangerous to conclude anything, because if 0.111 is extremely small, turns out to be extremely small, then negative 0.1111 might mean that it is not really a line, right? It just happens to be slightly below sea level. Anyway, to answer your exam question, if you are asked to calculate, then this is it. What if this example represents not a sample, but the entire population? All right. So if that is the case, most likely for academic reasons, because they want to test you whether you know how to apply the population covariance formula, then you are treating this entirety as all the data in the world that we care about. And there are 10 of them, 10 items. So we just apply the formula strictly. And in this case, mu x will turn out to be 8.6, because mu x is calculated as the average of the first column. It's the same calculation. The meaning is different because now we are treating the whole data set as the whole population. Well, so we write a different symbol, but for mean, the calculation for mean of population and the mean for sample is the same. So mu y will still be 6.5. And everything here actually will be the same. So in short, we just copy the -1 here. And instead of dividing by 10 minus 1, we just divide by 10. Right? So end up we get a different number. And careful here, it is not due to rounding problem. It's actually based on slightly different formula. So they'll be close by, but they will not be exactly the same. So the difference is not rounding, it's actually due to differences in the population. What if we have grouped data? Now you're going to see grouped data a lot, because data with many pairs of measurements, right? And occasionally the numbers will repeat as a pair, like what we saw just now, 97 and 97. So occasionally they will repeat, and you are unlikely to see data being presented to you like this with repetitions and all that. Maybe you see that being given to you in an Excel file, in an R file, in a data file, right? Maybe that's the case, then it will be just straightforward computation. But if it is grouped data, it will be likely grouped because the numbers are huge in number. So maybe it's 10 million pairs of data, right? So in that case, to present to you that 10 million, yeah, I'm just exaggerating the quantity, sets of data, usually it'll be in tabular form, in a table like this, right? So it'll be unique values of x in either the rows or columns, and unique values of y's in the opposite axis. All right, and then the proportion, percentage, or probability as they call it, will be given in the boxes. Of course, they will add up to 100% or 1. And that is to show the distribution of it. So group data distribution kind of one and the same, depending on the context under which they discuss. Calculation wise, same. If they call it probability, then of course the numbers must add up to 1, because the numbers will represent assumption that the future proportion will be the same. So it's probability. So how do we calculate that? There's no new formula based on the same formula, except we kind of tinker it a little bit to, so it goes from 1 summation to 2 summations, but there is actually no change in the mathematical implication. It's just trying to say, let's calculate the mean of x, all right? Then use 8 minus the mean of x times how likely it is going to occur, all right? And then calculate the mean of y, then 6 minus mean of y, 7 minus mean of y times the probability that it will occur. So that's handled by this joint probability here. So so we see the very core feature of covariance, right? The deviation from X mean and deviation from Y mean, and then multiply the two deviations together, then times the frequency of occurrence, the probability itself. That's it. So to make it a little bit more concrete, let's look at this example, right? So let's calculate the population covariance. Now, there will be no sample covariance when we are given a distribution, whether it's group data, distribution, uh, joint distribution, joint table, right? So long as it is distribution, we are informed that the data given has to be a population. So we'll calculate covariance, population covariance of X and Y. And how do we do it? Well, you will have to separately first calculate the mean of X, which is 8 times 4, assuming all Y variations are there, you add them all up, plus 9 times 0.6, right? Then you get 8.6. Then mu of Y will be 6, which is this, times across all X, you get 0.5, and 7 times all the probabilities across all X, you get 0.5. So 6.5. So once you get these separately, mu X and mu Y, you will then say 8, which is a value of X, 8 minus 8.6 times 6, this guy here. Oops. All right, so we have 8 minus the X difference, the mu of X, 6 minus mu of Y times this guy, right? Because it's 8 and 6, so it's 0.1. Then likewise, it's 9 and 6 times 0.4. 8 and 7 times 0.3, 9 and 7 times 0.2, as you can see here. So it's just point by point this stuff. It's useful to go through it point by point, at least for once, especially when you're picking up this calculation first time, right? Just to see how the numbers go. And you see that all points are covered one time and one time only. We never go back and let's say we include point 1 again the second time. Never. Notice that, right? So all cells are touched once exactly. If you happen to pull up the same number from any cell more than once, or skipped a particular cell completely, so 0, then it's wrong, confirm wrong, right? Unless the cell happens to be 0. So end up we get what? Minus 0.1. So end up being the same, because actually this calculation is based exactly on the original raw listing of the data.